Hello and welcome back to Engineering Problem and Solution. Today we're going to look at the topic called Transient Current Analysis of RLC Series Circuit. So today we're going to find the expression for the current and for that we're going to use differential equation solution. So first let's consider this circuit. So this is a RLC series circuit. So let's draw a circuit. So circuit has a resistor and then it has inductor, and let's apply the step voltage, and then we have the circuit. So let's say the step voltage of Vt equals to V naught is been applied, and R is the resistor, L is the inductor. So if we say current is going this direction, which is the expression we need to find, which is IT, then we can say our VR is plus minus here, and then plus minus VL over here. So basically what we're going to do is I'm going to show you three simple steps, and we're going to apply that three simple steps to find the transient current for the RLC circuit. So we also need to have initial condition. So let's provide the initial condition for this circuit is 0. So 0 plus I0 plus E0. And this is basically RLC circuit. In RLC circuit, your I0 plus and I0 minus are going to be same because of the nature of inductor. So I0 plus and I0 minus is technically same value. So let's apply the step 1. So let's say step 1. So in step 1, what we need to do is we need to apply the KVL in the circuit. So KVL applying, or we can say apply KVL in the circuit or in the loop. Now this is quite a good point to make a note of. Whenever you have a series circuit, the best way to solve the series circuit is applying KVL. KVL stands for Kirchhoff's voltage law, and it states that sum of the voltage inside a closed loop must be equal to 0. So if we apply the KVL in this circuit, in the loop, what we're going to see there is the voltage, which is V naught, is dissipated in the resistor and inductor. Means the voltage across VR plus VL is going to be the input voltage. Now once we have this, then we can further rewrite this in terms of current, because we need to find the current expression. So we know V naught is a constant, which is constant voltage in step voltage. And then VR is nothing but I times R. And then we have VL, whereas VL is nothing but L di L over dt. But since remember, this is basically, we can say here VL is L di L over dt. But this is a series circuit, so IR and the IL is same, so I'm using this IL as I in this equation. So if you look this is a differential equation. However, this is not a standard differential equation. To make a standard differential equation, we need to make sure that L is removed from here. So to get that, what we can do is we can divide both sides by L, and we're going to get di over dt plus R over L times I equals to V naught over L. Now this is our differential equation. So this is our differential equation, and we can say this is first order differential equation, for RL series circuit. Now this is step 1. So we are done with step 1, and then we'll move on to step 2. So in step 2, we're going to basically solve the differential equation. So step 2 is to solve the differential equation. Now to solve differential equation, we have different methods. It's up to you, whatever method you want to choose. You can use classical method, you can use power series method, but to make our life easy and to make things easier in mathematical term, we're going to use Laplace transform, because Laplace transform is quite handy and easy to use whenever is solving the differential equation. So solve differential equation, we're going to use Laplace transform. So we'll say using LT. LT stand for Laplace transform. Now, whenever we are using Laplace transform, we need to make sure that formula is with us. Now, if we look here, and we can write this equation. Let's write this equation is equation number 1. If you look this equation, we have derivative, which is di over dt. We have I, so this I is a variable, and then we have a constant, which is v naught over L. So there are 3 formulas we need to convert that into the frequency domain. Now, what is frequency domain? Basically, Laplace transform is going to transpose, or is going to change the time domain, whatever. So this is our time domain. Whatever we'll see this equation here, and whatever we do normally is all time domain. And transfer function is going to convert time domain parameters into the frequency domain. So we need to have a formula. So let's write the formula which we are going to use. So technically we need 3 formula. So I'll write that 3 formula. The first one is Laplace transform of derivative of di over dt. And the Laplace transform of derivative is SIS. And the initial condition I0 plus. Similarly, we'll need the Laplace transform of I. Normally I or IT, sometimes I write I or sometimes small I or IT, they are basically same. They will change into the capital I and bracket S. Normally, whenever you are doing frequency domain, if capital letter is indicated, then it is in frequency domain. It is not necessary you have to write S in the bracket. And the last formula we need to use is Laplace transform of constant. Constant is going to be constant over S. So this 3 formula is the formula we need to use in above equation 1 to solve the differential equation using Laplace transform. So what we're going to do is, let's rewrite that differential equation again, just to make sure that we can see that. So that is our differential equation. Okay, equals to v naught over L, and then applying Laplace transform on both sides. We get let's apply the Laplace transform. So we have L di over dt, and then plus we have a Laplace here. Now this R over L is a constant, it's not a variable. So when you have a variable and then constant together, you can separate this constant outside, because that constant is not going to play any role. So the Laplace of the first derivative is simply going to be SIS minus I0 plus. Similarly, we have this R over L is constant, and Laplace of I is going to be IS. You can write multiply here. And then we have Laplace of constant, which is V naught over L is constant, is going to be V over L divided by S. And then if we look at initial condition above, so initial condition is given us as 0. So the initial condition here, this value is going to be 0. So what we're going to get here is going to be S IS plus R over L IS equals to V naught over L divided by S. Now next thing which we can see is this IS and this IS is common there. So we can take IS common. The leftover is going to be S plus R over L equals to V naught over L divided by S. Now we can throw this to our right hand side. And we're going to get IS on our left hand side and everything on our right hand side. We're going to get V naught over L divided by S, and whole thing is divided by S plus R over L. So that is our equation which we get here. Now we can say this is our equation 2. We can say this is our equation 2, and we are done with step 2. Now we'll move on to step 3. Now some in a control system, if we have output over input, we call that is a transfer function. Now in some of the control system, we can use this relationship as a transfer function. So please make a note of that. Now furthermore, let's move on to the step 3, which is last step. So step 3. Now step 3 is all about applying the inverse Laplace transform and converting back our frequency domain, which is our this equation 2, into the back to the time domain, so that we can get a transient analysis or transient expression of the current. So to do that, we need to make sure that we're applying the inverse Laplace transform in a correct way. Now, if you look this equation 2, we can apply the inverse Laplace transform, but it's going to be a little bit hard because we don't have the standard format. Now, what I'm talking about is standard format is the formula. So we need to make sure that this complicated fraction is being separated in a simple fraction. So we need to apply the partial fraction rule or method to separate them in an easy fraction. So, but before we do that, let's write the formula which I have to apply here to go back to the time domain. So I'm going to use again 3 different formulas for here. So let's write the formula here. So the formula which I'm going to use for this example is going to be first inverse formula. I'm going to write here is 1 over S plus A. So I have to use this, which is going to be E minus AT. And the next formula which I'm going to use is going to be inverse of constant. So inverse of constant over S is going to be constant. So it's exactly like it's all the way around of Laplace transform. So the Laplace transform of constant is going to be constant over S, isn't it? Similarly, Laplace transform of E power minus AT is going to be 1 over S plus A. So it's all the way around. So those 2 formulas is what I'm going to use to get my final answer. But there is a problem here. As I said, the equation 1 is not a standard. I need to have a format like this, like some constant value divided by S plus A. A can be R over L or something, whatever. But I need to have a simple fraction like that, and same thing like that. So I need to have a separate of S and S plus R over L need to be separated. So I need to separate them in a fraction. So we have to use a partial fraction method. So what I'm going to say here is but equation 2 is in this kind of format, which is is equals to v naught over L divided by s plus r over L, which is not what I can apply for inverse Laplace transform. I need to separate them. So what I'm going to do now is applying the partial fraction. So if I apply a partial fraction, then I can take this fraction and then separate that into the two fractions. So how I can do that is I take the same fraction here, the main fraction, I would say the complicated fraction, and then separate them with a, which I would say s, plus b, s plus r over L. So what's the idea here? If you see here, this complicated fraction is converted into two simple fractions. So that's the idea. And you can see here, then I can apply this two formula here. This formula for this value and this formula for this value. So that's the idea here to do the partial fraction. Now, only thing which is holding us here is the value of a and b. We don't know what is the value of a and b. So we need to find the value of a and b. So how are we going to do that? To find the value of a and b, we can compare the coefficient of constant on the left hand side and the right hand side. So what we'll do first, let's simplify this and make a single fraction on the left hand side and right hand side. So we have on left hand side we have this main fraction, but in right hand side we have these two fractions. So let's combine them together. So we'll get denominator as like that, and numerator we have two different, which is a should multiply with this bottom bit. Okay, so I will say times s plus r over L plus b need to multiply this bit. It's like cross multiplication times s. Now to find the value of a and b, now what we can do is, we can simply compare the denominator on the left hand side fraction and the right hand side fraction. So what I'm going to say here is, let's compare, or comparing the coefficient of the s and constants. Okay, so first what I will do is I will take the left hand side and right hand side, the coefficient. Let's remove that. Left hand side and right hand side, coefficient of s. So if you look here, then I can clearly see that on my let me use this. So on my left hand side, on the top, on the numerator, okay, I'm just looking for the numerator side. I'm not looking for denominator. I'm just looking numerator because the denominator, they will cancel out each other. So I can get the value of a and b just comparing the top one for both. So on the left hand side, I don't see any s coefficient value. So that's going to be 0. What about right hand side? In right hand side, that a is going to multiply with s. That means I have a here, and then b is also there with s. So a plus b is going to be on my right hand side. Yeah, which is the coefficient of s. So that means I can see here that b is minus a. Yeah, we can say this is our equation 3. Now we need another expression or equation, because we have two unknown a and b. We need to have at least two equations to solve them. Now next one we can find is to compare the coefficient of constant, or constant basically mean that x power, you have a variable s power 0. So we can compare that. So again, if we say left hand side and right hand side, let's compare what is we have constants on the left hand side and the right hand side. On the left hand side we have this constant value, which is V naught over L, whereas right hand side we have a constant here, that's R over L, which is multiplying with A. That means we're going to get is on right hand side simply A times R over L. So this and this will cancel. L and L is cancelled. So the value of A is simply V naught over R. Yeah, which we can say equation 4. And then we can use this value for the equation 3, and we know therefore V is also minus V naught over R. So hence we got the value of A and B. So that means our fraction, our partial fraction has been solved because we got the value of A and B. So then we can say I, now we can say IS, which is A V naught over R divided by S, minus, which is B, because it was plus B there, so it's going to be minus V naught over R divided by S plus R over L. So we got this expression. Now we can clearly see this is the format we can apply the inverse Laplace transform. Or we can furthermore take a common, which is V naught over R as a common, and we can see is 1 over S minus 1 over S plus R over L. Now we can apply inverse Laplace. Applying inverse Laplace transform, we got inverse Laplace of IS. This is constant, and I'm going to say inverse Laplace for 1 over S minus inverse Laplace of 1 over S plus RL. Now we know that inverse Laplace of IS is simply IT, or I, a small letter I. I don't know why I use this as S. Should be R. And then we have V naught over R. And then inverse Laplace of 1 over S is 1 minus inverse Laplace of 1 over S plus R over L. If you look like the formula, where is our formula here? The formula is here. Our A value is R over L. That means it's going to be E power minus R over LT. So it's going to be E power minus R over LT. And then we can write this in a nice way, which we can say is V naught over R bracket 1 minus E power minus R over L T. And you can clearly see that time constant, time constant of RL circuit is simply L over R. That is can be seen from this expression here. So the unit is amps. I can write that. And this is, or we can say which is the transient current analysis solution of RL series circuit in 3 simple steps.